Hasan.
Hi.
And
So thanks for introducing me, and thanks to the organizers for providing me the opportunity to present my work. This is my first experience in presenting the work in the international conference in non-Hermitian physics. But basically, I will be presenting this is mostly the Hermitian work. And this was done in the supervision of my PhD supervisor, Professor Bhavani Prasad Mandal from BHU Varanasi. So the superperiodic potential, this is basically the generalization of the periodic potential, and starting from a unit cell potential, we show that the superperiodic potential is one of the most generalized form, and it has its application in the context of the similar structures, computing the tunneling amplitude from the self-similar structures. So this is the general graphical pictures for a scattering from a one-dimensional potential, where the coefficients from the left and right are connected together through the transfer matrix elements. In the context of the linear scattering theory in the today morning session, Ali Mustafa Zadeh introduced the transfer matrix, discussed the transfer matrix, where the coefficients of the transmission and the reflection coefficients from the left and right can be computed if you know the transfer matrix elements. In your notebook, you may see that the L and R might be changed here. This is because of the conventions, and the RL was with minus sign. But if you're taking the modulus square of that, then that thing goes away. So if you repeat the unit cell potential, then you have the periodic system. And in case if you know the transfer matrix elements of the unit cell potential, then in terms of the transfer matrix elements of the unit cell potential, you can compute the transfer matrix elements of the periodic potential. This matrix is from paper by D.J. Griffith, American Journal of Physics, 2001. In this, M11 is the transfer matrix elements of the unit cell potential, and this whole is the transfer matrix elements of the entire periodic system. U stands for the Chebyshev polynomial of the second kind, and the Xi1, which is called the block phase of the fully developed periodic system, which characterizes the band structure of the periodic system, is given by M22 cos alpha plus Ks1. If you take M11, then it will be M11 cos alpha minus Ks1, where alpha is the argument of M22. Now, you have the unit cell potential. You repeat it periodically, you get the periodic system. Now, the periodic system as a whole, if you repeat, you'll get another periodic system. That periodic system as a whole, if you are repeating further, and that periodic system as a whole, you are repeating further. And you are able to do this operation to an arbitrary number of the times. The number of the times that you are doing this operation defines the order of the superperiodic potential. So the scenario is like this. This whole system is V1. Now V1 as a whole repeats periodically with a difference periodic distance C2 or S2. Now this whole system V1, which already has the internal periodicity, call it as a V2, and the system V2 as a whole further repeats. Call the whole system as V3, and the V3 system further repeats. Do this operation to an arbitrary number of the times. The Vn is the generated potential Vn is the superperiodic potential of order n. The objective is to compute the transfer matrix elements of the superperiodic potential of order Vn in terms of the transfer matrix elements of the unit cell potential. The question is that can we do this? We did this problem. This is locally periodic. Yeah, but it will remain the finite if the number of the operation is finite, as well as the repetition is finite. That is why all these n times.
Okay, so n is finite.
N is finite, yeah. So M11n is this is the transfer matrix elements of the entire superperiodic potential. And I'm trying to compute the transfer matrix elements in terms of transfer matrix elements of the unit cell potential, which was just M11, M12, M21, and M22. So the diagonal and the off-diagonal elements, that M11n, this is the M11 is the transfer matrix element of the unit cell potential. This is the combination of the various NISI, and this is the product of the Chebyshev polynomial. The Xi1, Xi2, Xi3, Xi4 up to n is the block phase of the respective periodic system. So this is just one term here as a product of this. Xi1 will come in the next slide. This is another is a single term. Now there is another sequence comes. G1, G2, G3 goes up to Gn minus 1. This term, the sequence of this term depends upon its sequence. The number of the Chebyshev polynomial that it contains depends upon the terms R itself as well as the order of the periodicity. The off-diagonal elements are pretty easy to compute. The M22 will be the complex conjugate of this. This we have exclusively proven in our paper. M12, the off-diagonal elements are pretty simple. It is just the product of the Chebyshev polynomial, and there is the summation kind of the NISI summation comes here.
Excuse me?
Yes.
Here.
Yes.
I'm sorry, you might have stated it earlier, but what is the motivation of repeating these potential? Like,
it will come later. In the application section, I will discuss. This section will come. Okay. So the block phase xi, the block phase, the general expression is given like this, where in order to compute any xi n or xi j, you have to compute the each xi j minus 1. Is a kind of the recursive relation. So M22 is the M22 element of the transfer matrix of the unit cell, and alpha is the argument of the M22. This is the cosine term as a whole. If you know the N1 S1, I mean you know the structure of the SPP, superperiodic potential, then these things you have already characterized. Now this is, you can compute by the sequential operations, and this is again a single term, and the term H1, H2, H3 given as like this, which does depend upon the sequence itself as well as the order of the superperiodicity n. So that now, once we know the M22 elements, we can compute the transfer, the tunneling amplitude. We can take the 1 upon M22 and the modulus square of that. In the context of the periodic potential, when a single unit cell repeats n1 times, this we already know. M12, where M12 is the transfer matrix elements of the unit cell potential, and it has repeated n1 times. So this is the SPP of order 1, superperiodic potential of order n. Now, if you just, this system as a whole repeats n2 times, you have V2, n1, n2. And this formula simple, there is a simple generalization of the formula. This goes at the U n2 minus 1 xi2, where the xi2 is a block phase computed in the previous slide. And this keeps going. You have a very simple expression of the transfer matrix tunneling amplitude for a superperiodic potential. And this is very simple to generalize, provided you know the block phase of the various periodic system. Now, going to the application, it is an extraordinary fact to recognize that the fractals pattern, the self-similar structures, symmetric self-similar structures are the special case of the superperiodic structure. The simplest one-dimensional fractal is the Cantor one-third potential. You can take the black region as a rectangular barrier, and in the Cantor one-third, each stage G, you take out the one-third portion from the middle, and you keep going with the sequence G. The resultant sequence of the potential is called the fractal distribution. Basically, it's the fractal distribution, but in the context of the potential, I'm calling it the fractal potential. Now, please focus on this cell. I repeat it again. This is the rectangular potential, rectangular SPP of order 0. That means just unit cell potential. I repeat it again. N1 equal to 2 here. The whole system I repeat again. The whole system I repeat again. And the whole system I repeat again. So this pattern, this becomes the, in general, a general Cantor fractals. General Cantor means instead of 1 by 3, you are taking 1 upon gamma. A Cantor fractal potential of stage G is a rectangular superperiodic potential of order G. And our observation have suggested that the symmetric self-similarity is the special case of the superperiodicity. This is from by taking the different fractal distribution, say as the Smith-Volterra Cantor potential or the Pauli-Eddy Cantor potential. But this is yet to be proven mathematically. We have not done that. This is from the graphical representation of the 1D fractal potentials. We know this actually. And by using the SPP formalism, we have derived the closed form expressions of the transmission amplitude from the general Cantor fractal potential and the Smith-Volterra Cantor fractal potential. The Smith-Volterra Cantor fractal potential is a potential when you are taking out the 1 upon 4 to the power g fractions from the middle at each segment. So that means if you are taking the thinner and the thinner portion at each g, you are expecting that the transmission probability, the transmission profile as a whole with increasing g should saturate. Because at each stage g, you are cutting down the thinner and the thinner. We have provided the closed form expression in our paper actually here, but I am not giving the mathematical details here. So you can see that as we increase the G further and further here, the red, blue, and green curve shows that G equal to 6, 8, and 12. Nearly these curves overlap each other. To show the better resolution, I have taken the y-axis as this. T stands for, T lies between 0 to 1. So log of T for a better resolution, it will be negative actually. Take the further log of that, minus of this, you will get a positive quantity. You can see that several short features that exist, but with the increasing G, the transmission profile as a whole saturates. And we are working to generalize our work for the case of the general SVC potential, in which instead of 1 upon 4 to the power G, you take 1 upon rho to the power G. We have completed the mathematical expressions for that. And to the best of my knowledge and whatever my little experience is concerned, the SVC potential shows the some of the sharpest resonance from in the tunneling probability. This is really very sharp. Actually. Now coming to the some general features of the superperiodic potential. This one, many of you already know actually, that in case if you, this is the tunneling probability from the SPP of order n. So if any of the Chebyshev polynomial becomes 0, I mean at a k equal to kg star, if this is the transmission peak of SPP of order g, any of the Chebyshev polynomial becomes 0, then further to that, whatever the superperiodicity you add, the SPP structure will still show the transmission peak at k equal to kg star, provided the order j is greater than g. This holds for any pair of jj such that this, provided k equal to kg star is the transmission peak. Graphically, this is like this. Vg is a superperiodic structure, and there is a transmission peak, the plane wave is going. If k equal to kg star is the transmission peak, that means the wave fully passes through this. So it fully passes, so it fully passes. If it sees another potential again, it will pass through it. And no matter in whatever way you repeat the potential, whether you repeat the superperiodic manner, or you repeat the quasi-periodic manner, or you repeat the periodic manner, the wave will still pass through that. So the another feature of the SPP is the splitting of the transmission peaks. This you can prove by doing the perturbation analysis of the block phase xi-n. Now here is the double delta potential. The blue curve is the double delta potential. I have plotted the log of t. So t equal to log of t is 0 here. This is the transmission peaks actually. And this is when the double delta potential repeats 4 times. The blue curve is this. Xi2 is this, the argument of the Chebyshev polynomial. Now, if transmission peak at k equal to k star of the tn1, when the unit cell repeats n1 times, this term has to vanish. Then only you will have the transmission peaks. Now, near to k star, if you do the perturbative expansion, you can show that the xi2 changes sign due to the presence of the dominant cosine term here. When xi2 changes sign, whenever xi2 belongs to the closed interval of -1 to 1, the Chebyshev polynomial has the simple roots. As a result, you will have the n2 minus 1 transmission peaks near k equal to k star. This will not lie at k equal to k star. K equal to k star peak will be there due to the discussions done in the previous slide. That k equal to k star, the peaks, the wave will pass no matter how many times you introduce the superperiodicity. So the overall result is that if the transmission peaks get splits due to the superperiodicity. And if you repeat n2 times, you will see that there will be the n2 number of the peaks. All will lie between the range where the xi2 changes from -1 to 1. So this is the t24. Now if you increase to 40 times, you will see that there are the 40 peaks when xi2 changes from -1 to 1 over the range of j. So the transmission peaks gets replaced by the resonance band due to the superperiodic structure. Sometimes you may have difficulties in resolving these peaks. From here to here, there is a 1 million times zooming to see this peak. I was expecting 12 peaks here because of this. This is the rectangular barrier case, a double rectangular barrier repeated 12 times. So I was expecting the 12 peaks here, but I was not able to see it. So here to here is a 1 million times zooming to see the another hidden peaks actually. So our conclusion is that starting with a unit cell potential, the superperiodic potential is one of the most, if not the most, then at least it is one of the most general form of the periodic structure. And our observation suggests that the symmetric self-similarity in one dimension is a special case of the superperiodicity in one dimension. We have limited ourselves to one dimension, but of course the superperiodic concept you can extend to 2D and 3D case also. And by using the SPP formalism, we have derived the closed form expression of some standard counterfractal counterpotential and the Smith-Volterra counterpotential. And the transmission peaks, here is a word of caution actually. Not all the transmission peaks get split due to the superperiodicity. The transmission peaks that arise due to the periodicity gets split due to the superperiodicity. And our future plan is the extension of the superperiodic potential to the case of the non-Hermitian potential. And also to see that how the coherent perfect absorption points, the energy at which the CPA occurs, distributes based on the SPP structure, superperiodic potential structure. I mean, if we have the fractal potential, non-Hermitian fractal potential, does the CPA point distribute in a fractal manner over the K space? These things we want to explore further. And we want to explore the SPP structure in the context of the fractional quantum mechanics. In the fractional quantum mechanics, the band structure arises much faster with respect to the repetitions. So the fractional quantum mechanics will be discussed tomorrow by Professor B.P. Mandal. Thank you very much. The fractional quantum mechanics comes because the standard quantum mechanics is based on the path integral approach.
No, you have Cantor set. I mean, you pointed out Cantor type potential,
Yes.
which is a fractal structure.
Yes.
So is there any, so Cantor set is associated with chaotic behavior.
No,
So
no.
is there any kind of chaos that is associated with
No,
your
no, these
system?
fractal potentials, it is just the repetitions of the rectangular barrier in a certain fashion. So it is not related to any chaos.
Yeah, by repeating these potentials in the fractal type,
Yes.
what is the consequence to the transmission probability? Like,
Yeah, one thing is that one thing that I have discussed is that the SPP brings the transmission peaks, but it doesn't bring that in the context of the fractal potential, because in the case of the fractal potential, at each stage G, the unit cell itself changes. So it is just a new structure as a whole. But the fractal potential are known to display the self-similarity in the tunneling amplitudes, which is something as a very remarkable phenomena. And in the context of the it has been proven on the theoretical ground, it has been proven that the counterfractal potentials, its tunneling amplitudes show the self-similar structure. In the case of the SVC potential, we have seen some of the sharpest transmission peaks actually, which was in fact just taking few states G equal to 3 or G equal to 4. We see some of the sharpest transmission peaks, which we don't see in the case of the periodic potential kind of thing. And yes. Okay, okay. Yes, yes, yeah. This is what is done in the case of the fractal. The L is constant. The total length of the system is constant. You increase the G, you are keep decomposing the system. Yeah. So that is what when we did it for the fractal case, this is what we mean by that. But in the case of the counterfractal, if you do it for the infinite times, you are not left with any point. But in the case of the SVC potential, you are left with some point. But in the case of the SVC potential, it saturates.
so this can be done even for the large potentials.
Yes, yes. Large potential, you mean the spatial extent?
Yeah.
Yeah, yeah. Because all are the locally periodic, so N1, N2, you can change it to any numbers.
Okay, another question up there.
Do you get a version of Anderson localization in this superpotential?
Say it again.
Do you get a version of Anderson localization where
No, Anderson localization we have not explored actually.
If you would have Anderson localization if you had some randomness. But so you're saying if you had any imperfection, you would immediately get localization. Yeah, but it's going to be very unstable to imperfections, right?
Yeah, the fractal.
Mm-hmm. You can localize in a simpler way. You don't need to repeat it. But I wanted to ask another question.
Okay.
Can you write a recursion relation for the transfer matrices and then get the fractal limit as this fixed point of that equation? That's question number one. And question number two, in the fractal limit, can you summarize what the spectrum should look like? I mean, I'm not sure I followed you all the way to the end.
Relations has been done in the case of the fractals.
Say again?
The recursive relations has been done in the case of the fractal potential.
Okay.
Means the earlier formulations were based on that.
Yes. So, can you...
Not ours, but done by the different authors actually.
Okay.
Yeah.
And can you summarize in few words what is the spectrum in the limit of the fractal? What, I mean, the bound states, if any, the
spectrum
bands, the structure of bands, whatever.
No, the spectrum, by spectrum you mean here
the spectrum. in the limit of n goes to infinity, in the fractal. What?
You are asking for bound states, whether
The band structure. Well, the band structure.
Actually, it's a very vague answer. I'm not very sure about that. Which, if you increase the small n, like n1, n2, n3 is there. So capital N, small n. Small n is the order of the superperiodicity. If the small n you take to infinite side, the whole system resembles as a simple periodic potential of the unit cell as you repeated that as infinite times. This is what you understood. See, there is there is some potential which I have repeated as n1 times. Now this whole system, I have done the SPP part, and have done is as a...
Asking about the limit when you have infinitely many
Yes.
repetition.
So if you'd have the n tending to infinite, it has the same feeling as this tending to infinite. This is what I'm not very... It's not very concrete things here. Based on my experience, I have come to this understanding.
So if that's the case, what do you gain from your nested algorithm? I mean, in the end, the spectrum is the same.
Yeah, so you can see here is that, yeah, some of the ripples are actually very small. So in context of the band structure, like you see, this is just, everything is near to 1. In this domain, everything is just near to 1. And so these ripples are actually very small. So what happens is that if you increase this, what is near to 1 just become constant. And then there is a drop, directly drop. So the valleys, transmission valleys, are the precursors of the band structure. So it comes same as you increase n tending to infinite, or you go for the n1 tending to infinite. But I'm not, I'm again saying that this is some feeling which I have developed based on my experience.
But how can
But it's
that
not a
be,
concrete...
how can that be in the case of the Cantor set? I mean, is that what are you telling me, that in the Cantor set?
So in the case of the, yeah, in the case of the Cantor set, the unit cell itself changes. In the case of the SPP, it doesn't change. Yeah.
So what's the spectrum of the Cantor set?
So in the case of the Cantor set, the tunneling probability is known to have the self-similar structure.
Say again?
The Cantor set is basically a self-similar pattern. Cantor, this is basically a self-similar pattern. You can zoom any portion of that. Like if you zoom it properly, it will look like this. Okay. So the tunneling amplitude profile of T with K also looks like the same.
Claim your answer valid for the, your answer there is valid for that as well?
No, no. Because in the case of this, the unit self itself...
Okay, maybe I interrupt for a minute so that it becomes an extended discussion. Is there a question now, Michi, or you have a comment?
Actually, I once worked on electromagnetic transmission in the fractal pattern. Okay. And I computed also the resonance. And I wonder if you computed the, the amplitude inside the potential rather than the spectrum.
Amplitude?
Because I found that at exactly the resonance point, you have a very strong peak inside of the amplitude, inside the potential.
But here inside the potential, we have not explored anything. The T and R is defined with respect to the outgoing waves and the incoming waves.
Right, but the resonance is not the scattering wave, right? So outgoing wave, but inside you can compute the amplitude, right?
You mean the transmission resonance when you are talking the resonance?
I guess you're talking about the resonance state outside the potential. No, did you calculate the wave function inside the potential?
No.
No. I recommend you to do that.
Okay. All right. I think on that note, we'll conclude this session, and let's thank all the speakers for the day.